I'm Zach Strack, and this is Lab 2 Projectile Motion. What was our purpose today? A major portion of our curriculum at the start of the semester is focused on projectile motion and other changes in motion using velocity and position update formula. This was made mostly on Test 1. In this lab, we use position update formula and the velocity update formula, which are both derived from Newton's second law. What did we do in the lab? We threw a paper ball with a measuring stick to know the distance it traveled. We took videos of this and analyzed it using Tracker. We wrote code to simulate this projectile motion. Finally, we compared the results. What did we discover? An object moving in projectile motion moves in a parabola-like curve. With no drag, it's a perfect parabola, and the horizontal component of velocity never changes. And the vertical component accelerates at a constant rate of 9.8 meters per second squared. Introduce drag, and your object flies a lot less far, and the horizontal velocity decreases. The only equation we used in this lab was the position update formula, the velocity update formula, and the drag equation, as shown below. Why can we use these models? We can use these models because they are just applications of Newton's second law and still hold true under non-constant forces such as with drag. What was the experiment? The system was the ball, the surroundings was the air and earth. Initial conditions started tracking right after the ball was released. This data was from Tracker with y and x positions on each respective axis. Coding. First we set up plots for the position and velocity graphs. Then we set initial conditions like the position and velocity as found by Tracker. We set our loop to update the position at each time step, delta t. Finally, we printed the position of the ball at each time. The real versus the computer. The blue is the real found by Tracker. The orange is estimate with drag, and the green is no drag. There's many differences between these, and most of them can be summed up by human error. We couldn't get the initial conditions right or perfect, as you can see, or just drag was an estimate, it wasn't perfect. But the major thing that made the green arc so far off from the blue arc is that no drag was accounted for. What does this mean for us? Can we accurately predict projectiles without accounting for drag? Not really, but it depends on what accuracy you want. And drag affects lighter objects more like our paper ball, so it was a major factor. Do our models predict terminal velocity? Our model was getting there if we gave it more time. The curve never flattened out. Letting it run for longer, we can see the terminal velocity of our ball would be about -5 meters per second squared. Meters per second. What if we threw the ball straight up? If it had the same magnitude of velocity, then it would go higher and it would stay in the air for longer. But if only the y component was the same, it would go the same height and stay in the air for about the same amount of time. Thank you. This is it.